and welcome, my dear students. This is Laxman from EEE department, working as assistant professor in Mlritm. In this session, I am going to explain transformer operation under load condition. What is transformer? Transformer, it transfers electrical energy from one circuit to another circuit without change in frequency. See here, figure shows transformer and it carries two windings, primary winding and secondary winding. So the winding which is connected to supply is known as primary winding. The winding which is connected to load is generally known as secondary winding. First, I will explain what is the transformer operation under no load condition. Transformer primary winding is connected to supply V1, and here under no load condition means secondary winding is not connected to any load. A load means it may be resistive, inductive or capacitive load. So what happens when there is no load connected in the secondary winding? So here primary winding is connected to supply V1. So now this primary winding has a closed path. So definitely now in this primary winding some current is flowing. Okay, let me name that current as I0. I0 means no load primary current. No load primary. Since secondary winding is not connected to any load, so some current is flowing in the primary winding. This current is known as no load primary winding current. Now what happens when I0, that is this no load primary winding current, flows through the primary winding? Here the purpose of this I0 is used to meet two things. First thing is it is used to meet iron losses present in transformer. So I0 has two things or two components. One component is used to meet iron losses present in the core of the transformer, also known as core losses. Second component is used to meet flux in the transformer core, or it is used to produce flux in the transformer core. So I0 has two components. So overall I0 is nothing but Im plus Iw, two components. One component, that is Im, is used to meet or to produce flux in the transformer, and the purpose of Iw is to meet iron losses in the transformer core. Okay, this is what happens when transformer secondary winding is not connected to any load. Only I0 is flowing in the primary winding. Since secondary winding is not connected to any load, current flowing in the secondary winding is 0. Let me name secondary winding current is I2. So I2 is equal to 0. Secondary winding current, I2 stands for here secondary winding current. So this is what happens when your secondary winding is not connected to any load. So here I am explained briefly. Transformer operates on principle of mutual induction. When the secondary winding is open circuited, it is said to be on no load. Only the primary winding is connected to the AC supply. Since secondary circuit is open, no current flows in the secondary, that is I2 is equal to 0. Primary draws a small current. So current flowing in the primary winding, that is I0, which is very small when compared to full load current. So small current drawn by the primary under no load is called exciting current, I0. This I0 value is only 2% to 5% of rated full load current. I told you already it has two components. One is magnetizing component, second one is working component or active component. So I told you this magnetizing component is to produce flux in the transformer core, or you can say in other words, it magnetizes the transformer core. Another component is used to meet iron losses in the transformer core. See here, loss in the sense here heat. Some energy is wasted in the form of heat, okay, in core part of the transformer. Those losses are nothing but iron losses. So IM lags supply voltage by 90 degrees. I will show you what do you mean by this. IM lags supply voltage by 90 degrees and IW is in phase with supply voltage. So I told you I naught is equal to IM plus IW. Actually I naught bar is a phasor sum of IM bar and IW bar. So magnitude of this I naught is equal to square root of IM square plus IW square. Here it is written. IM produces mutual flux in the transformer core. This flux links both windings and induces E1 in the primary winding, E2 in the secondary winding. The purpose of IM is to produce flux in the transformer core. Now what happens when the flux flows through the transformer core? It links both windings, both primary and secondary winding. Now according to Faraday's law of electromagnetic induction, whenever there is change in flux linking with the conductor, EMF is induced in the conductor. So there is induced EMF in the primary winding and induced EMF in the secondary winding. Induced EMF in the primary winding is given by E1. Induced EMF in the secondary winding is given by E2. And you know, E1 and E2 lag flux by 90 degrees. Already we have seen the EMF equation of a transformer. There we derived this statement. E1 and E2 lag pi by 90 degrees. No current flows in the secondary when it is open. So transformer draws very small power from supply to compensate iron losses and to maintain alternating magnetic flux. Copper losses are negligible since I naught is small. Here we are not taking account of copper losses. Why? Because I naught is very small when compared to full load current. So I am neglecting copper losses. So major losses under no load are iron losses. So there are two losses in the transformer core. One is iron loss, second one is copper loss. Under no load condition, copper losses are very small, so even I can neglect them. So major losses in transformer under no load condition is iron loss. So this is the phasor diagram of a transformer under no load condition. So how to draw the phasor diagram? And we know, let me take this flux as the reference phasor. Why? Why? Because it is the flux, this flux which is common to both primary winding and secondary winding. That means this flux links both winding, primary and secondary. That's why I am taking this flux phasor as reference waveform. And from the EMF equation, we derived that E1 or E2. E1 or E2 lags the flux by 90 degrees. So E1 is the induced EMF in the primary and E2 is the induced EMF in the secondary. According we know that this induced EMF opposes the cause. So who is responsible for this E1 and E2? Supply voltage. So E1 and E2 opposes supply voltage. So I have to draw the voltage phasor, that is supply phasor, exactly opposite to your E1 and E2 phasor. Okay, this is V1 phasor. There is 180 degrees phase shift between V1 and E1 or V1 and E2. Now, we know that I naught, no load current, is having two components. One is IM and second one is IW. So IW is the working component. So it is used to meet iron losses in the transformer core. So that is loss component. Loss component in the sense that generally loss takes in place in case of resistor. We know the voltage current are in phase in case of a resistor. So I will draw IW in phase with supply voltage. Here IW is to meet iron loss. So loss in the sense here generally takes place in resistor. In a resistor, voltage and current are in a phase. That's why I have drawn IW in phase with supply voltage. Now where I have to draw IM phasor. See, primary winding is purely inductive circuit. So what is the relation in inductor? What is the relation between current and voltage in an inductor? You know that current lags applied voltage by 90 degrees. So since primary winding is, I can consider it as a purely inductive. So I have to draw IM phasor in line with flux phasor. That is IM lag supply voltage by 90 degrees, neglecting resistance of the primary winding. So I am considered the primary winding is to be purely inductive. So now phasor sum of IM and IW is I naught. So this is the way we have to draw the phasor diagram. So first we have to take flux as the reference waveform because it is common to both primary and secondary winding. Next, we know that induced EMF lags flux by 90 degrees. So you have to draw E1 and E2 phasors at an angle 90 degrees lag. According to Lenz's law, your induced EMF opposes applied voltage. So voltage phasor is 180 degrees, exact opposite to your induced EMF phasors. IW is in phase with V1. Why? Because this is IW is to meet iron loss in the transformer core. IM is to meet flux in the transformer core. So that's why I have drawn IM in phase with flux phasor. Now this is the topic today, operation of the transformer under load condition. Here I am not considering winding resistance and leakage reactance into effect. Okay, so I am explaining ideal operation. So now what happens when load is connected to the secondary? See here, I have connected now load in the secondary winding. So now because load is connected in the secondary winding, definitely some current is flowing in the secondary winding, that is I2. Why? Because now it is having closed path. Under no load condition, it is not having closed path. That's why there is no current. That is I2 is equal to 0. Now I2 is flowing in the secondary winding. Now what will happen when I2 flows in the secondary winding? See, now when connected to a load, I2 flows in the secondary winding. Now this I2 produces flux. Why? Because current carrying, we know that current carrying conductor produces flux. Now according to Lenz's law, what is the direction of pi 2 in the transformer core? We know that Lenz's law. What is the Lenz's law statement? Effect opposes the cause. Effect opposes the cause. So in simple word, Lenz's law is effect opposes the cause. Now what is the effect and what is the cause? Here effect is the pi 2 and cause is the pi. So here I can say pi is the main flux, or you can say this is working flux. Now what will happen according to Lenz's law? Effect opposes the cause. Here effect is pi 2, cause is the pi. So now pi 2 flows opposite direction to main flux. The direction of pi 2 in transformer core is in opposite to the main working flux. So I will show you in the diagram. So this is the pi 2 direction. So I have shown outside actually the pi 2, I mean this secondary flux, here pi 2 is called secondary flux. Now the direction of pi 2 is opposite to main flux. Now what happens? As a result, net flux in the transformer core reduces. Why? Because pi and pi 2 are flows in both opposite directions. So net flux in the net flux in the transformer reduces. Net flux in core reduced. So now what happened? As and when the resultant flux in the transformer core reduces, what transformer will do? In order to maintain that main flux constant, transformer draws another current from the supply, that is I1 dash. So why it is taking another current now? Why? Because of pi 2 which is flowing in the transformer core, the net flux in the transformer core reduces. In order to maintain that flux constant, your transformer take some energy from the supply, that is I1 dash. Here I1 dash, what is I1 dash? I1 dash is load component of primary current. I1 dash is load component of primary current. Load component, because this current came when the load is connected, that's why it is called load component of primary current. So as and when transformer draws this I1 dash, this additional current from the supply, we know that current carrying conductor produces flux in the transformer core. Now what happens? This I1 dash produces flux phi 1 dash in the transformer core. Why? Because current carrying conductor produces flux. Now what is the direction of this flux phi 1 dash in the transformer core? The direction of this phi 1 dash is opposite to pi 2. So why? Because again same reason, Lenz's law. Effect opposes the cause. So effect is here, pi 1 dash is the effect and pi 2 is the cause. So the reason for getting this pi 1 dash is pi 2. That's why according to Lenz's law, pi 1 dash opposes pi 2. So both pi 1 dash and pi 2 are in opposite direction, and this pi 1 dash cancels the flux pi 2 in the transformer core. So the only flux flowing in the transformer core is the main flux. Okay, what I am saying is here, when the load is connected, pi 2 flows opposite to the main flux direction. As a result, net flux is decreasing. In order to maintain that flux in the transformer core constant, transformer is taking another current, that is I1 dash. This I1 dash produces pi 1 dash. Now that pi 1 dash opposes pi 2 or cancels the effect of pi 2. So remaining flux is pi in the transformer core. So the important statement is here, when the transformer is connected to no load or connected to load, the flux in the transformer core remains constant. Okay, this is the very important point. So here I have explained what I told now. So when load is current, I2 is flowing in the secondary. I2 produces demagnetizing MMF which opposes the main flux. To maintain constant flux, the primary draws additional current I1 dash such that MMF in the primary winding is equal to MMF in the secondary winding. So now what happens? This ensures that net flux remains nearly constant. So the total current in the phasor sum is I1 is equal to I0 plus I1 dash. So when the transformer is connected to no load or load, this current remains same, I0. So the additional current is I1 dash because of load connection. I1 dash is in phase opposition to the secondary current. Okay, this is the operation of a transformer, phasor diagram of a transformer under load condition. See here, I have taken load, inductive load. This is the example for inductive load. So in inductive load, we know current lags voltage. So what is the current flowing in the secondary winding? I2. So what is the induced EMF in the secondary winding? E2. So I can say I2 lags flux, phi2, I2 lags E2 by some angle, phi2. So in exact opposition to I2, we have to draw I1 phasor. So already we have seen what is I0. So the resultant of now I0 and I1, I0 and I1 dash is I1. So I1 dash is phasor sum of I0 and I1 dash. Okay, this is the case for inductive load. Okay, now here I have taken resistive load. This is a phasor diagram for the resistive load. We know that in a resistive load, voltage and current are in phase. So I2 is in phase with induced EMF in the secondary winding. So where I have to draw I1 dash? I1 dash is exact opposite to I2. Now phasor sum of I0 and I1 dash is again I1. That is the total primary winding current. I1 is the total primary winding current. Now this is the phasor diagram for the case capacitive load. Here I am not saying purely capacitive, I am saying just capacitive load. In a capacitive load, we know that current leads voltage by some angle. If it is a pure capacitive load, it leads capacitive load by, it leads voltage by 90 degrees. That I2 is the secondary winding current. Now it leads E2 by some phase angle phi 2. Now in opposite to I2, I have to draw I1 dash phasor. Now combination of I0 and I1 dash is I1, total current in the primary winding. Okay, this is how transformer work under no load and load condition. So in this session, I have explained what is the operation of a transformer under no load condition, and also I have explained how to draw the phasor diagram of a transformer under no load condition, and I explained what happens when load is connected to the secondary winding, and also I have done phasor diagram for taking by considering different loads, that is capacitive load, resistive load and inductive load. Okay, that's all for today's session. Thank you.